Good morning, everyone. Can you hear me? Yeah, nice. It's not too close to my mouth again. Yeah. So I continue talking about OCT actually today, but we'll focus on SPECKLE. So I'll try and give an introduction about SPECKLE, just the very basics of SPECKLE, enough for us to understand what is a fully developed SPECKLE, and then we'll relate it to the SPECKLE we see in OCT images, and then show what SPECKLE can do for us. So SPECKLE is somewhat a noise pattern. Nowadays, it's hard to define it as noise because it's so useful for a lot of things. But back in the first experiments with lasers, it was really just noise. Like, it was hard to avoid it, and it was not the focus of the experiment. And it's very granular, so the appearance of the SPECKLE is something like this. The contrast here is not great. But you can see it's very high contrast. A lot of bright and dark spots appear on the surface. And you can kind of think right now, like bright and dark spots, this seems a lot like the interference. We talked about it yesterday. And we'll see it's actually exactly that. So it's usually associated with coherent, like highly coherent light source. It's high contrast, as I said. You have a lot of dark and bright spots. And the first studies on SPECKLE pattern began soon after the first laser applications, when it was really easy to visualize them. Well, the origins of the SPECKLE is actually light scattered from diverse points on a surface. So if the surface is rough, like the surface has height variations, and it has to be rough on a scale of a wavelength, so that's pretty easy to obtain, you have wavefronts coming from different parts of the surface. And these wavefronts actually interfere with each other before they reach observation point. And yeah, this interference between waves generates these bright and dark spots. So here's an illustration by Professor Goodman, which is pretty much the reference for SPECKLE. And you can see here, on a direct observation, you have the rough surface, and you have different contributions coming from different parts of the surface. So each wavefront we hit here with a specific phase, and they'll combine each other to form either a bright or a dark spot. When you're imaging now with some sort of lenses here, that may be your eye actually, and all you have to all that need to occurs for you to have SPECKLE is that more than one wavefront reads within a resolution cell of your system out of phase. So you can have these bright and dark patterns. However, since it's a combination of multiple wavefronts, SPECKLE is pretty much a random phenomenon. And the intensity at any resulting point on your observation plane is the result of many, many scatterings on the surface. So this intensity can only be described statistically. And Professor Joseph Goodman actually did a lot of these statistics back in the day, and they're still used today. So for this lecture, and just for us to understand a little bit about the properties of the intensity, you're just going to talk about the first order statistics. So this is the very base of SPECKLE. It's not really that hard. There's just a lot of assumptions being made in order to derive the statistics of first order. So now, one thing that we have to assume is that we are actually dealing with many scatterings. So there's many individual random parts contributing to this intensity. And it's pretty much a random walk problem. So the resulting amplitude at any point would then be a combination of many phasors. You can describe it, each one with their specific phase. And in order to derive the statistics, Professor Goodman made this assumption that the phasors amplitude and the phase, the amplitude and the phase for each phasors are independent of each other and independent of other phasors. Also, the phases of these phasors has to be uniformly distributed on the interval of -pi to pi. He made these assumptions in order to assume these properties. So the real and the imaginary parts of this resulting amplitude will be uncorrelated, have zero mean, and identical variance. Now, assuming that, and if you have a very large number of phasors, which is usually the case, you can use the central limit theorem, and then you can express this as a sum of very large number of random variables for the real and imaginary part. And by the central limit theorem, you have that the real part, the amplitude, and the imaginary part of the amplitude are asymptotically Gaussian. So the joint probability function will be this Gaussian right here, and the variance will be pretty much the average of the amplitudes. Why do we care about this joint probability? Because we care about the intensity. And what we're going to do now is try to relate intensity into this joint probability. So we rewrite the amplitude, the real and imaginary parts of the amplitude as a function of intensity and the phase. So intensity can be expressed by the sum of both real and imaginary parts. The phase is just the tangent minus 1. So now the probability, the joint probability of intensity and phase will be the probability of the real imaginary parts right here, modulated by the Jacobian for the random variable transform. The Jacobian is really pretty messy because it's the partial derivatives, a matrix of partial derivatives. But in this case, it's pretty simple because the equations we are dealing with here, there's just two variables and pretty simple equations. And the resulting from the Jacobian is actually pretty simple, it's just 1/2. So now we can rewrite the joint probability function as a function of intensity and a function of phase. So this is this Gaussian right here now. And we'll exploit it a little bit further and try to get the marginal probability density functions. So for the intensity and for the phase. For the intensity, it's a negative exponential expressed here. And for the phase, it's uniformly distributed, as we would have expected, in minus pi to pi. Now, since this is exponential negative, a negative exponential, sorry, we can deduce some things about the end moment, which will be given by this equation. And we can exploit this just a little bit further and show that the standard deviation will be equal to the average intensity. Now, this means that the signal-to-noise ratio, which is just the standard deviation divided by average intensity, is 1 for the SPECKLE pattern. And this is a pretty good way of measuring contrast. Now, any SPECKLE pattern that obeys these basic statistics, that obeys these assumptions made by Professor Goodman, are usually called as fully developed SPECKLE pattern. And those are the types of SPECKLE patterns that have pretty much all the statistics derived for them. Let's write that. Now, another interesting thing about the intensity, about SPECKLE pattern, is that this pattern that you observe is very dependent on the surface that's originating it. So changing the object that is originating the SPECKLE, changing your illuminated object, actually causes changes in the pattern observed. Even more interesting is that very small displacements for these objects actually make the pattern move with them, so they remain correlated for very small movements. And that's the basis for techniques like double exposure speckle photography you can use to determine local movements in a sample. Now, for larger displacements, the intensity actually decorrelates with time because of the movement of the surface. And that's the point that we are interested in in SPECKLE, because if we observe a single point in the plane, your observation plane, this intensity will fluctuate over time. And since these fluctuations are caused by the movement of those patterns, movement of these objects, you can somewhat relate the fluctuations over time to the velocity of this movement. So this is right here, sorry. So these fluctuations that you're observing may reveal information about the velocity of the object. And there are techniques developed for that. So now, SPECKLE is no longer a noise for your system. It's actually an information source. And I put this here. I'll not go into the discussion, but just point out if anybody's interested. Some people, some researchers actually theorize that Doppler shifts and SPECKLE pattern is just the same thing, observed from different perspectives. So there are further readings for you. of course, Professor Goodman is the reference, so either his chapter in the laser speckle and related phenomena book, or say his manuscript, which is pretty much basically the same properties derived for Optical Society of America. And this is a work by Professor Breers that actually gives an explanation of this view of laser Doppler and time variance speckle as the same thing. Now, as I said, temporal analysis about this intensity may reveal information, additional information, which you usually don't get about the sample. So how can we do that? So in a simple experiment, you can imagine that you're illuminating a target with a coherent light. So you're using optics to illuminate a very large area. So you image it, and for now, let's imagine that you're just not imaging it with your eye, but with some camera. And now imagine that parts of the target are moving. And your camera has a fixed exposure time. Now, what happens is, since the target is moving, the fluctuations of intensity are occurring over time, and this occurs inside your exposure time. So now you're integrating a lot of different intensity fluctuations. What happens in your image, in this case, is a loss of contrast. It's a blur in your image. So now, if you can quantify this blur, maybe you'll be able to relate it to the velocity of those fluctuations, right? And that's the basis for the single exposure speckle photography technique. So this technique is proposed by Professor Furcher and Breers back in '81. And the aim is just exactly that, how to quantify the blur. So we can get information for then was mainly about circulation in samples, so microcirculation. And one way to quantify the blur is actually related to the signal-to-noise ratio of the speckle pattern you're observing, which is the concept I just derived with you for the first-order statistics. So now they also make a lot of assumptions to get to the result, but I'll just show you basically what they are doing for this technique. So they are getting the optical variance, they're getting the spatial variance for the image, so the spatial distribution of intensities in the image, and relating it to a temporal optical variance of the signal they're imaging. Now, the optical variance, the temporal optical variance, is given by this formula. Is basically the autocorrelation normalized, so you can normalize it by intensity square. Now, you can relate the optical variance with the autocorrelation intensity by this formula right here. And if you assume the Sigurd relation, which is used a lot in dynamic light scattering experiments. So if you assume a Sigurd relation, you can relate the second order autocorrelation, which is what we have, so the autocorrelation of intensity, to the autocorrelation of your field, so the first order autocorrelation. Usually there's a constant here multiplying this autocorrelation function, but they assume for this case that this constant is 1. Now, we can begin substituting back these equations. So now you can have your autocovariation normalized, defined by your autocorrelation of the first order. And if you go back substituting again, you can define your autocovariance non-normalized by this autocorrelation of the first order. And then you go back even further and say, oh, maybe we can assume, and that's another assumption they make on their work, that depending on the velocity distribution you're observing, you can expect this autocorrelation for a signal to follow a negative exponential defined by this tau c here. So this tau c is the main point of their technique. So this is, sorry. Oh, I thought it. I forgot to add that text here, just to make sure it's explicit. So this tau c right here is the correlation or correlation time. So it's the time for then, the time it takes for this exponential to fall to 1/2 of its original value. So this decorrelation time, you can kind of relate it to the velocity because it's making the autocorrelation go fall either slowly or very, very, very fast. So now you begin substituting these back in your equations, and then you can substitute back even more and get your spatial variance, which is what we are measuring in your image, defined as a function of this autocorrelation of the first order. Now they make another bold assumption here, so they assume ergodicity for the system. And what they do is they substitute the average intensity in time for the average intensity in space. And now they can kind of describe this equation as a function of the signal-to-noise ratio, so as a function of contrast. So now you can measure this quantity in your image directly and relate it to the tau c, so related to the velocity of the scatterers of the, sorry, not yet scatterers, of the movement of your sample. So this is right here. So this, this is the graph of the experimental values against the theoretical values for this tau c. So this is just the contrast they are measuring against the correlation time ratio to the exposure time. So this is interesting, right? It's not following perfectly, but for some measurements, for their measurements, it's good enough. What happens here, however, when the correlation time is much, much, much longer than your integration time of your camera, you kind of miss a lot of these fluctuations. So your system gets saturated, so you can no longer differentiate velocities if your correlation time is long enough. The same thing happens if the correlation time is short enough. So this is around 0.4 for their experiments. So if the correlation time is much, much shorter than your integration time, then you can no longer differentiate these flows as well, because these fluctuations become decorrelated in time. Now, they've done all of that on this technique, basically an analog manner, and they later, Breers again with Webster now, they devised a digital version of it. So they called it LASCA back in the day, so laser speckle contrast analysis, and nowadays just mainly refer to laser speckle contrast imaging. So this is basically the digital version of this technique. But what this technique really measures is just this. So it's the spatial variance over the spatial intensity average. And how can you do that in an image like digitized manner? So it's pretty simple. You can get any sliding window of pixels and apply it to your image. So you can just apply it here. And usually you don't use any information where your window doesn't fit inside your image. You can do that, it's just unusual. So you ignore this first row, and the sliding window goes away, and you don't use anything of that. But now your sliding window fits inside. So now what you do is you basically just get the intensity for each pixel, calculate the average, and then calculate the standard deviation. And then you make the ratio and make it as a new pixel in a new image. So you keep doing that for for all your pixels of your image, and you create a new image that is basically a contrast analysis of your image. You can make it go for any map color you want. This is usually the case, or red is a lot of flow, and blue is no flow. And you can get images like this. So this is a very naive implementation of the LASCA technique. So you can see right here, it's just a human hand illuminated with a coherent light. And now you can see some information of flow occurring in the hand. So a lot of flow in the tip of the fingers, a lot of flow right here in the thumb, and no flow at all at the table. So the speckle fluctuations here are not occurring, or occurring very, very, very small amounts, and fluctuations here are occurring very, very, very rapidly. Now, we are interested in OCT, right? So how can we relate that to the speckle we see in OCT images? So as you can see from this image I just shown you, you can assume that speckle does not come only from the surface, right? If you are imaging microcirculation, you have to assume speckle comes from inside your surface as well, so inside your sample. And the speckle originated from inside the sample is what is of interest for us. So if you want to image microcirculation, especially in OCT, since you're doing in-depth measurements, you want this speckle coming from inside the sample. And for that, you can imagine the sample as a collection of individual scatterers. So you imagine like you have a cup with a lot of balls inside, so you're getting a lot of wavefronts coming from each of these balls, so each of these scatterers, and they are creating a speckle pattern. And as Professor Smith puts it, the word coherence in OCT is a primary strength and a primary weakness of the technique, because it's the coherence that allows us, as we've seen in the last lecture, is the coherence that allows us to get the phase of the cross-correlation term in the intensity equation. And that phase gives us information about depth in OCT. But it's that phase as well that gets affected by SPECKLE. So now you can have in-depth information, but you're also susceptible to SPECKLE, even though you're using a low coherence light source. You have a coherence window, so you kind of filter out a little bit of SPECKLE because you're filtered out by coherence timing, so coherence gating. So anything that arrives in your detector out of the coherence time of your system will not contribute to your signal. But for most biological applications, it's a densely packed scatters, so there's a lot of waves coming from multiple scattering centers, so you usually get a lot of SPECKLE for that. Professor Smith, Young, and Young made a very good work in SPECKLE in OCT back in the day, and this is a very good reference to study a little bit more. And that's the source of this image, actually. So what are the origins of SPECKLE? What are the main origins of SPECKLE in OCT? So you have the wavefront coming in from your sample arm, right? So you're imaging your sample. Now you have a lot of scatterers in your volume of interest. We have a lot of scatterers going through your volume of interest. So some of these scatters make forward scattering, so it creates random delays on your wavefront. There's multiple back scatterers. So one scatterer of interest actually scatters back to another scatterer. It scatters lights back, and that creates a phase variation as well. And even sometimes you have some scattering coming from outside of your volume of interest. And this also creates those aberrations in your wavefront. So these phase fluctuations, which are not good at first. However, the main source of SPECKLE in OCT is the multiple backscatter inside the volume of interest, because this is not a very common occasion, and this gets filtered out mostly by the coherence timing. Now, you can imagine that all it takes for SPECKLE to form in OCT is that these waves out of phase reach your detector inside the coherence time of your system. So this is very analogous to the traditional SPECKLE, because traditional SPECKLE, you have to have two waves coming out of phase inside your sample resolution, and now it's just out of phase inside your temporal resolution, right? But that does not mean yet that this is truly analogous to the fully developed SPECKLE. So the assumptions we made for the truly developed SPECKLE are here again. So you have to have a rough surface to create these phase variations. You have to phasers amplitude the phase independent of each other, independent of other phasers. You have to have phase uniformly distributed in the interval of -pi to pi, and you need a large number of phasers. And now those first two are actually kind of common for OCT. So rough surface for OCT is just two scatters separated by like a wavelength. So this is pretty easy to obtain. And large number of phasers also pretty easy to obtain, because most of your samples, especially biological ones, are very, very heavily, densely packed scatterers. And now Professor Smith, on his work, actually shown that the other two assumptions are also hold true. So you can see here is just a random walk of the real and imaginary parts of your magnitude in the OCT system, and the phase of your signal coming from the OCT signal, from the OCT system is pretty much evenly distributed. So it's a constant distribution from -pi to pi. So we now can somewhat justifiably think about OCT as a fully developed SPECKLE source, so you can make measurements with that. So just for completion, they also derived the probability distribution of the magnitude of the SPECKLE signal. It's somewhat related to the intensity distribution that Professor Goodman derived. It's close to a Rayleigh distribution. The signal-to-noise ratio they measured is on average 1.4 for system, for OCT system, but they say, Professor Smith say in his work that this varies a lot, especially for biological samples. And of course, like once you kind of justifiably can imagine your system as being a source of information for the time varying SPECKLE, as you just seen, you can explore it in OCT, and that's exactly what happened. So what is an easy way to do that in OCT? You have to understand now, in OCT, we don't have the exposure time of the camera, so you don't have the motion blur. What we actually do is observe the intensity fluctuations over time. So you acquire multiple times of the same, multiple B-scans, multiple images of your same location, very, very fast in time, and you can see the fluctuations happening whenever there's flow in your sample. One way to analyze these fluctuations is, of course, again, variance. Instead of spatial variance, now we use time variance. So you have a single pixel in a specific time, you obtain an image, and you annotate its intensity. You repeat that for a lot of different times of acquisition of the same position. So now you have the average intensity, and you can calculate as well for each pixel the average standard deviation. And now you can create the same kind of speckle contrast, but only now it's in time and no longer in space. So this is the basis for a technique called speckle variance OCT, which is pretty much the sparkle that started a lot of speckle measurements in OCT. And this is just speckle temporal variation. It's very simple, but they managed to get pretty good images. So this is an example of very naive interpretation of the speckle variance in OCT. So this is the tip of a finger close to your fingernail. And in the intensity image, you can really tell whether there's flow in that sample. However, when you do the speckle variance, this is a pretty naive interpretation, so this is like very low contrast yet. But you can see that some spots, like some very, very bright spots, appear in your image. And those are microcirculations, right? So those are veins in the tip of your finger. Now, just keep in mind for now, I'll talk about that actually at the very, very end of the presentation. But see that for each of those vessels, so each of the vessels you can identify with speckle variance, there's this trail, right? So that's an add fact. I'll talk about that later. Now, this is the original work for the speckle variance OCT. Is by Maria Ply, and they managed to get some pretty good images. This is the image I've shown you on the last slide of the last lecture. So they used the mice model. They used a window chamber to image it. And this is the fluorescence image, and this is the speckle variance image. Right, so this, you can see like speckle variance offers you a lot of details of microvasculature in much, much deeper structures. You can visualize it with other techniques. So you can see it's pretty detailed, right? It's very, very good. It's also independent of angle. So here you have the Doppler OCT, and here you have the speckle variance OCT, and they are increasing the angle of the beam to the flow until it's transversal to the flow. And you see the Doppler is just lose the information completely, but speckle variance, you retain information. However, it's non-direction and non-quantitative yet, right? And this very first frame here is actually at 0 millimeters per second. So even when there is no flow, if you have like any fluid here, Brownian motion will actually cause the correlation enough so you can kind of detect the fluid inside the sample. So this is another example they used in their study. They induced an ischemic reaction in one of the veins, and you can see it recover in time. So you can follow real-time angiographic measurements. So another, I'll begin talking about applications now because I think that's the focus now. Another interesting study is spectroscopy speckle variance OCT. So they used a chicken embryo for that. It's pretty interesting. They wanted to see oxygenated blood. So you can remember that hemoglobin, oxygenated hemoglobin have different absorption curves according to wavelength. So they derived two methods to actually acquire this information from OCT, either through a slide Gaussian window with OCTA scans, so you can kind of use a Gaussian to envelope different wavelengths of your source. So now you can have like different spectrum contributions for a single light source. And another technique that's a little bit faster is just to use two Gaussian envelopes directly on the interferogram. So they selected two bands inside the spectral distribution of the light source and compare, like, for each of these bands, they generate a new image. So they compare the signal for different longer and shorter wavelengths. Here they make an average according to a specific wavelength. And here they just take the ratio of two images they generate. And they extract absorption information based on the signal difference from longer and shorter wavelengths with OCT. As you see, this gives like a very confusing image. So that's why you need a speckle variance. Like you can detect the vasculature and use it as a mask. So here's their model. This is a chicken embryo model. This is an OCT. This is a single frame. This is an average of 20 frames or 50 frames. I can't remember right now. And you can see the structures of your microvasculature right here. And you can see an artery right here. It's pretty big. Now, the SPECKLE variance images for this very same B scan. This is just calculated over 20 consecutive B scans, and this is 100 consecutive B scans. So you can see you improve the signal-to-noise ratio because you average out your noise in the background. Now, this is the phase difference between the two wavelengths information. So it's pretty hard to analyze it like this. If you're average enough, you can kind of begin to see here that there's some flow going on, but it's pretty hard to visualize. So they use SPECKLE variance as a mask for that. So here they just threshold out the veins in the SPECKLE variance image, and they use it as a mask. And now you can map, color code your phase difference into different images. And you can see the difference of oxygenated blood flow and no-oxygenated blood flow based on the phase difference. So they managed to get spectroscopy information to a single light source with OCT, combining it with SPECKLE variance for masking. There's many different types of calculations you can do to actually pinpoint the fluctuations. You don't have to calculate variance. That may be time-consuming. So a lot of different proposals have been made. We explored a different proposal as well. So instead of calculating the variance of intensity, you just calculate the pairwise difference intensity in two images. And you multiply it, here this is the same equation, right? It is just explicitly saying that, oh, we are multiplying it by the original intensity, so you kind of improve your contrast because low signal regions will contribute less, even though the fluctuations may be larger. So this is the B-scan we used for a study. So this is a static reference in your frame, and this is a microchannel we developed in our lab. So it's a square microchannel. And there's flow being pumped here. We used milk here for scatterers in the flow. And this is the result. Like, we can get pretty good results regardless of low flow or very large flow. And this static reference gets filtered out because they don't have much fluctuations. So this is just comparing like the naive implementation of SPECKLE variance and our implementation. We get a pretty big boost in contrast in the images. However, you can still see those trails I talked about here. And compared to the naive implementation, we get the reduction in processing time because for the SPECKLE variance, you need the intensity average information. So it's a two-pass calculation. You can have one-pass variance calculations, but they're prone to a lot of catastrophic errors. And this result is actually easy to parallelize for computation in GPU or heterogeneous processing. We did that as well. And it's equivalent in memory allocation for processing against the SPECKLE variance. Another pairwise comparison for fluctuations in time was proposed by Professor Yaligia. And so you can see here it's pairwise because we are no longer scanning through multiple times, just comparing the frame at n and frame at n plus 1. And this was proposed by their work in 2012, which is the split spectrum amplitude decorrelation in geography. Now, the very interesting part about this study is not even this new definition for SPECKLE decorrelation, it's actually the split spectrum part. So they managed to come up with this solution for some sort of noise in the system. So usually the cell resolution for OCT is anisotropic. So your resolution in the axial direction, which is given by your coherence gating, is much, much higher usually than your lateral resolution given by the diffraction limit. What they did then is actually using a bandpass filtering across the spectral distribution for the light source. So now you can split your spectrum into different bands. Each band now, since your full width half maximum will be shorter, each of these limited bands, you have a very isotropic resolution. So you kind of decrease your axial resolution to make an isotropic pixel, and that removes sensibility to bulk motion occurring in the axial direction, which is a pretty big problem for OC and geography. And also, since you're splitting your band into like different, your spectral source into different bands, you can generate a new image for each band. So as you've seen, for us to acquire fluctuation information, intensity fluctuations, you need a lot of samples from the same location. And now you can like have 4 many times the number of samples you acquire with a single scanning. So you acquire 4 different images for each time you scan laterally your image. So now you increase your number of samples, and you can use that to reduce noise in your system just by averaging. And these are some results they got with this approach. So this is the structural one. And here are 2 different projections, so different layers of DI. So this is the optical nerve head. You can see right here pretty detailed information about vessels. And you can filter out, since it's depth resolved, you can filter out different depths, so you can highlight different vasculatures. It's pretty interesting, and this is very easy calculation. You can do it very, very, very fast. You can use even image like very deep in the sample. So now this is a foveal vascular zone, this is the macula. You can see like different aspects of DI with this approach. And you can see the bed of the choriocapillaries, which is very, very small veins. So you can see the fluctuation in time caused by the very end of your image. It's pretty interesting. Now, it's showing you ophthalmology, and actually, as I said before, OCT is a major game changer in ophthalmology. Ophthalmology is a major application of OCT. And while I was at Professor Fujimoto Group, I've been to ophthalmic conference then, so ophthalmology conference, a pretty big one in the US, one of the biggest. And over there, like over 80% of all the studies in the conference were using OCT. And this is an ophthalmology conference, a clinical conference, and over 80% using OCT. And that 80%, over like 90% were using angiographic measurements. So for ophthalmology, the term for this SPECKLE variations analysis I collectively called OCTA, so optical coherence tomography angiography. So this encompasses a lot of different techniques, but I'll refer to as OCTA. I'll show some more applications. So Professor Yalija again, now using the same technique to measure optic disc perfusion in glaucoma. So if you remember from the last lecture, I've shown you some diagnostics made in glaucoma with OCT using Doppler flow. And now you can visualize it pretty easily. So you can see right here in the optic discs, you can see in this image mainly, you can see the reduction in blood flow in a normal eye and a diseased eye with glaucoma, right? And right here, it's pretty obvious as well. So now, not only quantification and not only not only Doppler information, you can visualize the disease in real time, in vivo, and no other technique allows for that. And with optical disc flow index, so calculating an index based on the correlation of these images, they managed to completely separate in their study the normal eyes and the glaucoma. So it's a pretty good diagnostic technique. So in a recent work by Professor Fujimoto Group, I helped in this work. So instead of just measuring blood flow, we were actually measuring the areas between blood flow, so the ischemic areas in the eye. And this is a pretty good indication for retinal diabetic retinopathy. Sorry, diabetic retinopathy. So this is the major source of blindness in the US and worldwide. And what we did is basically, you have a manual phase to remove some artifacts, which are pretty common in OCT. I'll talk about that just a little bit further on. And now you try to fill out any ischemic areas based on your projection of OCTA images. And these ischemic areas, the total sum of those areas are related to the progression of diabetic retinopathy. You can have a further correction if needed, and then you save the data. So these are some examples across different stages of the disease. So this is a diabetic patient with no diabetic retinopathy, and you can see like there's almost no to no ischemic areas in the eye. Now, if you have the non-perfusion, the non-perfusion variation of diabetic retinopathy is the beginning of the disease, is non-proliferative as well, non-proliferative, sorry. So you can kind of see a little bit of ischemic errors popping up, so the microcirculation begins to get compromised, and for the proliferative version, you have a lot of ischemic errors, so this eye is very, very much compromised. And you can use the measure of these areas to try and separate different groups, so no disease versus disease. We didn't manage to get the statistical difference for non-proliferative to proliferative because we had very small number of subjects, but we didn't manage to get diagnostic, so diabetic retinopathy, any case versus no diabetic retinopathy, and we managed to get the area under curve for this diagnostic technique to be 0.93 using wide field images. So these images, as you can see, are very large at the eye. So this is one of the major applications of ST now. You have very large field of view for the eye, so you can see different aspects of the eye in the same image. So you can see the optic nerve head, the foveal vascular zone, among other things. So unfortunately, of course, since this is a fluctuation information in time, you are affected by a lot of different artifacts in your images. So some artifacts in OCA are mainly like low OCT signal. So if you have low intensity signal to begin with, you have low OCTA signal as well. And that may be falsely interpreted as no flow or impaired flow sometimes. And for wide field imaging, as was the case, you can get vignetting occurring with obstruction of the OCT being by the eye itself. You have projection segmentation. So those images are projections, right? Remember OCT, we are acquiring like each line here in depth, and then you scan to get this 3D projection, and then you project some depth of it into a single image. And this projection can cause a lot of artifacts, especially if you're using like some automatic approach to define the layers that you want to project, and this can cause a lot of artifacts in OCT, and that's a major problem for OCTA images. You have signal roll-off for OCT, so when you go in depth, your signal is smaller, and you also have some sort of trouble trying to visualize microvasculature very deep. You have a lot of problems with sample motion. As I said, sometimes you're making measurements in vivo, and sample motion will confound your algorithm because your fluctuations are occurring in a pixel in an image, and then another pixel in another image because the image has shifted upwards. And you have shadowing and trading. So this is what I was talking about when I said, like, no, you can see those trails behind, underneath the vasculature. Since the light passing through the vasculature is already decorrelated, it will begin decorrelated underneath it. So what happens is that you can exactly pinpoint where the vasculature ends because the light begins to decorrelate inside it, and then it's still decorrelated after the vessel, for instance, is no longer present. And this creates this tails effect. And they also create shadowing. So since the light here has already decorrelated, any other vasculature underneath it may be missed because the decorrelation trail and because the shadowing artifacts. So this is a pretty big problem and an unresolved problem as of now. So this is a major search for a simplistic approach to overcome that. For more information about like OCTA artifacts, there's a pretty good manuscript of Professor Fujimoto and Professor Spade, and there's a scientific report we wrote. It's being published now. It's still not published, but specifically addressing artifacts in wide field imaging. Now, you can also not only map microcirculation with SPECKLE, you can also quantify that. So as I said, you can imagine justifiably so that there's a correlation between velocity and the decorrelation time of your fluctuations. So it's mainly related to the transit time of the scatterers through a voxel of your image, right? So if the scatterers are moving very, very fast, you have some sort of signal. If the scatterers are moving slowly through your voxel, you get a signal that's completely different. So the autocorrelation approach, I use it for that. And the autocorrelation time variance spectroscopy will yield information about the velocity of the scatterers. So Professor Bowles has already shown you his approach to that. I was going to show you, but that's not fair. I'll show you another approach, autocorrelation approach. But there's the DLS approach for Professor Bowles. Nicholas Weiss in the Kaufman group also made some autocorrelation determination for OCT signal. to try and pinpoint different aspects of the vasculature, so of the flow. So it's also based on the DLS model, and they account also for different velocity parameters, as I'll show you here. But they do not account for particles entering and leaving the volume of interest, and they assume stationarity of the flow. So their autocorrelation approach is mainly composed of 3 different components. So there's a component for a Brownian motion or diffusion with a negative exponential. You have some Gaussian for transverse motion of scatterers, and you have this integral here, which is for the actual motion. And this is just basically a Doppler phase associated with the coherence gating. So this is related some sort to the Doppler discussion in time variant speckle discussion. Well, what they can do with that? So they can pretty much follow the transversal, the blood flow gradient inside a circular vasculature, inside a circular phantom. And this is just the Pauli spectral density. So you can see the spectral getting larger as the flow gets higher. So you expect more fluctuations to generate more higher frequencies in your spectrum. And this is exactly what they're showing here. And they managed to get pretty good flow information. However, you need calibration for the system. So you can tell the flow velocity unless you calibrate it priorly. Professor Ricky Wang and his student V. Wang actually had another approach for that, which is much simpler, and it's faster. However, you lose a lot of information, which was just an autocorrelation approach. They assumed a triangular autocorrelation function because they were assuming the particles contributing for the time variant speckle to be square pulses. So they assume a triangular autocorrelation function. And they just calculate the slope for the autocorrelation function. So they fit 2 points, the 0 leg of your autocorrelation and the leg of the first 0 that occurs in your autocorrelation. And they calculate this slope. So it's pretty straightforward, it's pretty fast, and you kind of get some sort of information related to blood flow. So you can no longer devise what each component is, so you lose a lot of information. But for fast measurements, this is pretty useful. You also did something like this. So it was an adaptation because we wanted a simple observation parameter, as Professor Ricky Wang had done. But we wanted to base it on more recent estimates of the autocorrelation. So we came up with different observation parameters. Instead of the slope, we are going to watch the time it takes for the autocorrelation to fall to 1/E of its original value, because we can relate it to the width of the Gaussian autocorrelation. And this is our result. So you can see here for different flows, the autocorrelation falls with different speeds. And the 1/E approach allows you to get some sort of information across different flow, even for very high flow information. It saturates around 10 microliters per minute. And we did some sort of B-scan. So this is not as pretty as it could be because we were not using a circular phantom. We were using a rectangular microchannel because we were trying to analyze the microchannels developed by our group with femtosecond laser. But you can see here, this is close to the wall of the microchannel, and the correlation time is pretty much longer, and then you get pretty much shorter as you go to the center of the microchannel, and then you get lower again as you approach the second wall. We use the same approach now also to measure the correlation due to Brownian motion. We wanted to try and come up with a way to measure glucose in vitro. Hopefully, we can come up with a way to do that in vivo sometime. But yeah, what we based that off is that we wanted the autocorrelation approach. So the autocorrelation is sensitive to Brownian motion, right? And by the Stokes-Einstein equation, you know the viscosity of a medium affects the diffusion coefficient of the medium. And glucose in the blood affects its viscosity, so we can kind of hope that glucose in the blood will affect the autocorrelation of the OST signal. We also did a spatial analysis, and this is just based off coefficient attenuation of attenuation coefficient across depth. So you expect glucose to have an effect of the attenuation coefficient of the blood samples, and it's actually true. We show that as well. But I'll just show you the temporal approach here. And we get a pretty good linear relation between blood glucose and the decorrelation time as we estimated. And you can visualize it in false color information here. So this is very, very low decorrelation time, and this is very, very high decorrelation time. You can see across different groups with different glucose concentrations, you get a shift in the color that you see. And finally, I just want to talk about one final work that is also somewhat quantifying, but you just want to get a measure of high versus low blood flow and not try to pinpoint, this is just the last application, and not try to pinpoint specifically what velocities are. And this is the VISTA approach proposed by Woo Choi and Professor Fujimoto group. It's called variable interscan time analysis. So basically what you do is change the time between consecutive acquisitions of the same location, what that does. So you can imagine it right here for a very fast acquisition speed. When the flow is very low, you can resolve it very well, mainly because your scatterers don't have moving so slowly through your voxel that they don't produce an appreciable decorrelation signal. So you have just a small window of blood flow velocity that you can measure, that you can actually produce appreciable decorrelation. Now, if you increase the time between scans, you give more time for this slow flow to cause decorrelations in your signal, and then you can image very, very low flows. But now your system saturates pretty fast, so higher flows are no longer the system no longer very sensitive to higher flows because they just decorrelate away. But you can see here, you get different information, right? So this is a very fast interscan time, and you can see in the yellow arrows, there's a lot of empty spaces that are no longer empty when you increase the interscan time. So you give more time for this slow flow to be captured by the OCT technique. And in a separate work, they just show you that this is somewhat related to blood flow information because you can see that there's, this is false color, there's the ratio between slow and high interscan times gives you some sort of information of blood speed. And you can see this higher speed for major vessels. And when you have some microaneurysms, as here, you can see the blood flow impairment in them. But it's pretty hard to analyze this image. It's still under discussion in Professor Fujimoto's group. And that's it for this presentation, but there's so much more for SPECKLE as well. Different techniques that can employ SPECKLE analysis, and there's different approaches to SPECKLE analysis. I've shown you like intensity approaches, autocorrelation approaches. There are phase variance approaches as well. So there's much more, and I highly encourage anyone interested in geography to take a deep look at SPECKLE imaging and for any technique. So once again, I'd like to thank FAPESP for supporting me throughout my master's and PhD, my home institution, the Nuclear Energy Research Institute, and University of São Paulo in São Paulo campus. I'd like to thank again the organizing committee and all the staff here for receiving me, and also again all of you for sitting through this another lecture, and thank you.
Thank you, Lucas. Any questions? Question here.
Thank you for the great lecture. You have mentioned before that there are some artifacts due to motion or low signal. But I was wondering, like, do you know any methods how to distinguish between the artifacts and the signal due to blood flow or something?
So depends on what technique you're using, right? If you're just mapping for the correlation ones, you can try to use, like, for actual motion or bulk motion, you can have some sort of image registration algorithm. You can kind of compensate for that. It's not great, but it works at some extent. What is usually done on clinical setups is that the system itself can see if the repeats of the same location are way too much shifted. And that's the case, the system itself repeats the imaging without telling even the operator. So the system itself will resample. It's usually the best case. But if you're using like quantifiable information in the autocorrelation approach, you can sort of distinguish between transverse and axial motion. So you can just take a look at the transverse resolution and say, oh, this is probably like, I only care about this motion, not this motion, so it will be less affected.
So is it a basic version of motion tracking that you perform on the images?
Sorry, I didn't get it?
Is it a basic version of motion tracking that you do on the images?
Motion tracking.
Right.
With SPECKLE? No, but just particle tracking in Israel.
I mean, with the overall image that you obtain, do you perform some motion tracking where you identify
Oh,
the features?
for compensating for motion.
Right.
Yeah, yeah. So that's basically what the registration algorithm does, just that you're based off your motion tracking on your surface usually.
Yes, but I was wondering, like for motion tracking, you need to have this assumption of brightness constancy, where the intensity, pixel intensity is assumed to have the same value as that of the next frame. But when you are dealing with SPECKLE, the assumption won't hold true. So I was wondering, how do you like compensate for that as well?
For the fluctuations in intensity.
Right.
Some registration algorithms are just based off cross-correlation approach. So you kind of move your image across each other until they kind of fit together. So the static features are going to stay the same. So your cross-correlation will have a peak when you're some sort in the same position. So that works pretty neatly.
Okay. Thank you.
More questions? So let's thank Lucas again.
Thank you, guys.